Good evening. Today is the seventh lecture on ship propulsion. Please pay attention. We are dealing with ship propulsion. The screw propeller of the ship, the details of the ship propeller. Now you can see this drawing. First we show you how the positioning of the propeller behind the ship. So you can see here we have the hull itself, which is on the blue line, and then we have the rudder at the aftermost part. So we have the propeller. Okay, this is the propeller here. The propeller is connected to the outer stern tube, right? And then there's a bearing, and this strut is holding a pipe we call the tube, the stern tube, in which the propeller passes. This is a twin screw arrangement, where the propeller is not at the middle, at the center line, but at the side. So we have the tail shaft, the stern tube, the inner stern tube, the seal that seals water from entering into the hull. Then we have the couplings. This part is called the intermediary shaft. We have three intermediary shafts here, and then we have the tail shaft. That is the arrangement for a twin screw shape. In a twin screw shape, see the propeller on this side, looking at it from behind, from stern to forward. You are facing the stern. The rotation is clockwise on this side and anti-clockwise on this side. You can see from the gearbox, clockwise and anti-clockwise. Okay. Now, these are the space. There must be a space maintained between the hull and the propeller and the rudder. A, B, C, D, E, and F. See, these are given by classification society. Here, DNV gave these values in this form for a single screw shape. For a twin screw shape is different, and it depends on the classification society rules and regulations. Okay, let's look at the propeller as it is. We have here all numbered. 1 shows you the diameter of the screw propeller, looking at it from stern. It circumscribes a circle, perfect circle. You have the diameter. Then half of the diameter, of course, is the radius. Then the rotation, this is the rotation, number 11. Then this side is the stern. Here is the face of the propeller. This is 4. Number 4 is the back. You see, number 5 is the face. Number 3 is the face. Number 4 is the back. Okay. Now we have the face is this side and the back is on the back side. So this face side is the pressure side, while the back is the suction side. Okay. All right. And the number of blade here, as you can see, is 4. So that is how the thing is defined. And here is written exactly what it is like. The diameter, the radius, the blade face, the back, the leading edge, and then the trailing edge. We will see more of it in the drawings below. The number, the blade tip, the hub. The hub is, the hub where all the blades are attached. The root is at the root of the blade, before the hub, where the blade is attaching to the hull. Then the propeller can be a right hand, as I saw you, or left hand. In a screw, you can have a left-handed screw and a right-handed screw. Still, they are all going forward. So here is additional. You can see the rotation. This one is clockwise, and this one is other. This is the chord section, as it is called, because it is aerofoil sections at different blades, at different radii from the center. This is the center, so this is the expanded view, and then this is the axial view, and this is the elevation, cutting it longitudinally. So this is the shaft on that side. So you can see the back, you can see the face, you can see the section through the middle maximum thickness portion. So this is like a drawing of this, what the drawing of the propeller looks like. Okay, now we can still go ahead explaining it more. This one now is rotating anti-clock, shown as direction of rotation is anti-clockwise, and here is the leading edge, following edge, pressure edge at the front, and then we have at the back suction side. So, and that's how it is. To explain it, this is the blade, the blade tip, from where the diameter is being mentioned. So you can see the blade section. When you cut it from some point, you get the section. The sections are different from the beginning to the tip, so that's the sections, and then these are the blade sections. So if the direction of rotation is in this way, you see, the angle of attack to this blade section can be measured, and from there, that's why we say this is the pressure side and this is not the pressure, this is the suction side. So here there's more, it is here that pushes the vessel, develops the thrust. Okay, all right, and then this is the pitch angle, and which we can now get the pitch, but we will see more about the pitch as we go down. The pitch times the number of revolution, which means okay, you can see here, this is the radius again, this is the longitudinal projection, and these are leading edge, trailing edge, as I've shown you before. And now, coming to some definitions, we have the diameter, we have the pitch ratio, which is pitch over, pitch over the diameter. Every screw have a pitch. The distance it will make in one revolution is the pitch. Assuming you are boring a wood, when you turn one revolution of a screw, it goes the pitch distance. Okay, this is the blade thickness ratio. This is the disc area tip. This is the developed area of the blade. Developed area ratio, DIR. That is the projected area against the developed area. These are parameters of the propeller, and it's based on these parameters the propeller is designed. So these are the projected area of the blade on transverse plane. This is the projected area ratio, AP over AO, projected area against the disc area. Okay, the disc area should be pi r squared, but the projected area is according to from the rear blade projection. Okay, this is the blade width ratio, maximum blade width against the diameter. Where is the maximum blade width? Let me go back again. I will show you what it means by the maximum blade width and the other one here. You see, the blade width is from here to here, section width. This is the maximum here, okay, against the diameter of the vessel. Okay, that's the blade width, maximum blade width, against the diameter. Look at it here, maximum blade width against the diameter. So we have mean width of blade, which is AD over the length of the blade. These are all ratios describing the propeller, so that we can get a good description of the propeller. And this is the, when the blade makes screws round, one rotation, it gives you what? The pitch. 2 pi r rotation, it moves the distance given by the pitch. But if you watch here, if the screw propeller is being screwed on a wood, definitely it will cover, if you screwed it n times, it will cover p times n distance. But inside behind the ship, you know, it is screwing the water, so it cannot be able to make the full distance, because there is what we call slip. The water slips. The water is not solid, so we have slip, then we have speed of advance. You see, I mentioned to you speed of advance before, VA. That is it. It is the pitch times the number of revolution minus the slip. You get the speed of advance. Okay. And then this angle is called the pitch angle. This angle, which is given by Pn over 2 pi r, which is here. That's the pitch angle. The slip will treat more of this in your handout anyway, but you can see the slip is ms over ml. That is the slip, and it's given as Pn. You can see Pn minus V against Pn, which can be further treated as this. This is what we call the slip. So the slip can be calculated, you know, as VA over Pn. P is the pitch, N is the number of rotation, VA is the speed of advance. Okay, we have met this speed of advance before, so when you know it, it's easy to calculate the speed. So a screw propeller, there are screw propeller models of different shapes and sizes and ranges of parameter listed above. These models are tested in the cavitation tunnel, as well as self-propelled open water tests to get charts, you know. So just like we make two models of ship and then use hydrodynamic theory to compare between the model resistance and the actual ship resistance, the same thing is done with the propeller. They use a small model of the propeller, throw it in a cavitation tunnel or in a self-propelled arrangement, and they will now get the force, the thrust it can develop, and then use hydrodynamic theory comparison to see what it will give for the actual ship. That is how, so they produce charts from which we can be able, just like we had we can get from the resistance test for both, the same way we get resistance test for, thrust test for propellers. And then this propeller must have a particular shape, and the shape is as I have already described to you. And then those are the parameters with which the shape is being defined. So there are different models, so which means you can get so many, just like you can have so many different designs of ship body from the body lines. We can have different designs. So also we can have different designs of propellers. For instance, we can have these screw propellers of different type. For instance, we have Wageningen series of propeller. We have AU series of propeller. We have GAN series. We have MS series. We have KCS series. We have SKU KCS series. We have NR series. We have the NASA. You know, this American. The NASA is the same they use for aircraft profile. But here it is also the blade section is shaped according to a NASA definition. Then we have the new foil and this. You can be able to try to browse all these different models to see how they look in actual sense. Thank you very much.